Hey Chemistry, welcome to Gases Part 2. So we are going to continue right where we left off, page 388, under gas pressure. Alright, so if you were to walk across deep snow in boots, you would probably sink into the snow with each step. Not that we would know that because we live in Florida, but you can imagine, I'm sure. With a pair of snowshoes, like the pair pictured in your book on page 389, you would be less likely to sink. In each case, the force with which you press down on the snow is related to your mass. Right? The heavier you are, the more force you're going to put onto the snow. Therefore, pressure on any given area of the snow would be reduced if you had snowshoes on and you spread out your exact same mass over a bigger area. Pressure is defined as force per unit area. Okay? So, how do the size and style of shoes you wear affect the force you exert on a surface? Think about it. Gas particles exert pressure when they collide with the walls of their container. Because individual gas particles have very little mass, it only exerts a little bit of pressure. However, there are probably about 10 to the 22nd particles in a liter container. That's half of a 2-liter soda. With this many particles colliding, the pressure can be substantial, which is why when you open some sodas after you've shaken it, they explode. In chapter 14, which is the next chapter, you will learn how temperature, volume, and the number of moles affect the pressure that a gas exerts, but we're not going to talk about that just yet. Earth is surrounded by an atmosphere that extends into space for hundreds of kilometers. Because the particles in the air move in every direction, they exert pressure in all directions. This pressure is called atmospheric pressure or air pressure. Right? At the surface of the Earth, air pressure is approximately equal to the pressure exerted by a 1 kilogram mass on a square centimeter. Okay? Air pressure varies at different points on Earth. At the top of a mountain, the mass of the air column pressing down on a square centimeter is less than the pressure at sea level. Thus, air pressure at high altitudes is lower than it is at sea level. So, measuring air pressure. You have an Italian physicist, Torricelli, who was the first to determine that air exerts pressure. He noticed that water pumps were unable to pump water higher than about 10 meters. He hypothesized that the height of a column of liquid would vary with the density of the liquid. So to test it, he designed equipment shown in figure 13.5 on page 389. It's this complicated little U-shaped system. Torricelli designed this, and he filled a thin glass tube that was closed at one end with mercury. While covering the open end so that no air could enter, he inverted the tube and placed it in a dish of mercury, so he flips it. Okay? The open end was below the surface of mercury in the dish. The height of the mercury in the tube then fell, because mercury is denser than water. And so the question was, did it support his hypothesis? The device he invented is called a barometer. A barometer is an instrument used to measure atmospheric pressure. Okay, the exact height, so as Torricelli showed, the height of the mercury was always 760 millimeters. The exact height was determined by two forces. One, gravity exerting a constant downward force, and two, an upward force with the air pressure on the surface of the mercury. All that to say, changes in air temperature or humidity cause air pressure to vary. An increase in air pressure caused the mercury, in this case, to rise, and a decrease caused it to fall. Through this, they were able to come up with another device called a manometer. In a manometer, you are able to use to measure gas pressure in a closed container. In a manometer, you have a flask connected to a U-tube, not Y-O-U like the thing that you're watching this on right now, but U as in the letter U as in U-shaped U-tube that contains mercury. In one picture that you can look at, there is no gas in the flask. The mercury is at the same height. But if you see when gas is put into the flask, the mercury changes height. Released gas particles push down, and so then looking at the difference in height based on when there's gas there, you can realize that gas does exert pressure. So all that to say, gas exerts pressure. Air pressure exists and is a thing that affects us, and we can use air pressure to predict things that are going to happen, like the weather. So, units of pressure. Let's talk about them. The standard unit of pressure is the Pascal. Yes, like the cute little chameleon in Tangled. 1 Pascal is equal to a force of 1 Newton per square meter. Okay, so a Pascal equals 1 Newton per square meter. A Newton is a unit of force. Okay, many fields of science still use more traditional units of pressure. For example, engineers usually use PSI, or pounds per square inch. If you've ever filled up your tire on your car, you'll see pressure in pounds per square inch. The pressure measured by barometers and manometers is usually in millimeters of mercury, which is mmHg. There's also a unit called a torr, which is named after Torricelli, the guy that did all the stuff that we just talked about. 1 torr is equal to 1 mmHg. At sea level, your average air pressure is 760 mmHg when the temperature is 0 degrees Celsius, or 32 degrees Fahrenheit. Air pressure is often reported in a unit called atmospheres. 1 atmosphere is equal to 760 mmHg, or 760 torrs, or 101.3 kilopascals. So there's all these units to measure the same type of thing. Why isn't it standardized? Because people disagree on which way is best. Okay, so use the table on page 390 to kind of understand how things work between an atmosphere and between a Pascal or a kilopascal. Okay, so because the unit's 1 atmosphere, so 1 atmosphere equals 760 mmHg, millimeters of mercury, which equals 760 torr. Those are defined units. They have as many significant figures as needed when used in calculations. Okay? So those things all equal each other. And they, in turn, equal 101.3 kilopascals. There we go. Okay, so Dalton's law of partial pressure. Let's use all of that and talk about when Dalton studied the properties of gases, he found that each gas in a mixture exerts pressure independently of the other gases present. So if you have lots of gases in a mixture, they're all exerting their own pressure. Okay? Dalton's law of partial pressure states that the total pressure of a mix of gas is equal to the sum of all the pressures. You're going to like this equation. Okay? So your pressure total equals pressure of gas 1 plus pressure of gas 2 plus pressure of gas 3 plus pressure of gas 4, so on, so on. However many gases you have is how many pressures you have. If you only have 2 gases, you only add 2 together. That's simple. Just addition. Okay? You got this. P total represents the total pressure. P1, P2, they represent your gases. So let's go through an example. 391. So we have a mixture of oxygen, carbon dioxide, and nitrogen, and you've got a total pressure of 0.97 atmospheres. Okay, so practice. So you have a mixture of oxygen plus carbon dioxide plus nitrogen gives you a total pressure of 0.97 atmospheres. Okay? If the partial what is the partial pressure of oxygen? If the partial pressure of carbon dioxide is 0.7 atmospheres and the partial pressure of nitrogen is 0.12 atmospheres. Well, let's figure it out. So we have O2 plus 0.7 plus 0.12 equals 0.97. So that means O2 equals 0.82, plus 0.82 equals 0.97. So we do minus 0.82 minus 0.82. We end up with oxygen equals 0.15 atmospheres. All it was addition. Okay? So, make sure, yeah, did that right? Cool, perfect. So, let's do one more example together, kind of reminding you that it doesn't really matter what the unit is. This whole thing, you just add it all together. All right? So now we're going to do practice problem number 4 on page 392. So, what is the partial pressure of hydrogen gas in a mixture of hydrogen and helium if the total pressure is 600 mmHg and the partial pressure of helium is 439 mmHg? All right, so we want to know, we've got hydrogen and helium. So hydrogen, helium. We want to know the pressure of hydrogen. We know the pressure of helium is 439 mmHg. and the total equals 600 mmHg. So we've got hydrogen plus helium equals total. Hydrogen plus 439 equals 600. Minus 439 minus 439. We end up with hydrogen equals 161 mmHg. So again, all we did was addition, okay? All we did was addition and subtraction. You got this. So now, with the other video combined with this video, you should have enough information to complete today's Junipod, which is due tomorrow. All right? Good luck. You guys got this. Let me know if you have any questions, okay? Bye.